Hey everybody, Mr. Piercy here, and we're going to be looking at some basic differentiation rules. This is where we're going to kind of step away from what we've been doing with the limit definition of the derivative and the alternate form of the derivative, and we're going to actually get into some derivative rules. So this is the fifth section in our Unit 2 material, and we're starting it off pretty basic. The first thing that you're looking at here is if you're trying to take the derivative of a constant. So the derivative of a constant, what it's telling you in the box here is that the derivative of a constant is going to be 0. Keep in mind, a derivative being the slope of a tangent line, well, the only way that you can be tangent to something that's already horizontal is to remain horizontal. So here, all of these derivatives, because they're simply constant values, a, b, c, and d. Even d, they're trying to throw you off a little bit, but k is just a number, and pi over 2, we're not looking at anything, with our, x variables or anything like that. All of those values are going to be constants, so their derivatives are 0. And that'll be useful when it comes to using the power rule or looking at polynomials where we're trying to take the derivatives. The next thing we're going to be looking at is a single variable. So if you have a single variable like what we're looking at here in these three examples, a single variable, whether the variable is x or whatever, has a slope of 1. And what we're going to see, especially when we get into the power rule, this is really going to start to make sense. Every variable that is just a single variable by itself is always going to have a derivative of 1, and that really has to do with the fact that here this has an exponent of 1. And so what you're going to see in the power rule here shortly is that the exponent here is going to get multiplied to whatever coefficient is in front of your variable. And so if the coefficient in front of the variable is 1, then 1 times 1 is just going to give you a 1 in return. So here are the derivatives for the three examples that we have here for a single variable derivative. Now we're getting into some good stuff with the power rule. What it's telling you here in the box, this is really good information. What they're showing you here is that we take whatever the variable is and it gets multiplied to whatever number is in front of your constant, or whatever number is in front of your variable, I mean. And then we also take that same number and we subtract it by 1. And that's kind of what they're illustrating here by putting the, oops, and I didn't mean to make that so dark, by kind of putting that in front of the x there and saying n minus 1 on the exponent there. So let's take a look at a couple of examples here and see, can we use the power rule? Usually kids pick up the power rule pretty quickly, but sometimes we need a little bit more practice, particularly on problems like C and D. So for A and B, we're going to just run through these quickly. We're going to take the variable that's in front. Oops, and I don't mean to have my highlighter still on. Let me go to my pen. I'm going to take this 2, and it gets multiplied to whatever's in front, so I get y prime will be equal to 2x. And the exponent will drop a value. We subtract that by 1, so 2 minus 1 gives me something to the first power. Or more typically, you would just say y prime is equal to 2x. And x squared, that's a polynomial, so we're going to be using the power rule a lot with polynomials. Anytime you ask to, at some point you're going to be so happy, you're like, yes, a polynomial, I can finally do the derivative in my head. Other times you're going to be struggling a little bit. So here on B, we're going to say f prime of x, and that would give us a derivative of 4x to the third power when we follow its derivative rules. Now the next two are going to change things up a little bit. We're still going to be able to use the power rules, but keep in mind that here, well, I don't want to put that there. Let's say y is equal to, we can rewrite the square root of x as an exponent and say it's square root of 1/2. Well, if it's a square root of 1/2, now we can use the power rule, where I'm going to say y prime is equal to multiply the coefficient to the the coefficient to the exponent, and that'll give me 1/2 x, and then we say subtract the exponent, by 1. So 1 minus, or 1/2 minus 1 will give me a negative 1/2 for my exponent value here. Well, of course, we don't leave things in terms of negative exponents, so we would say y prime would be equal to, we're going to move the negative exponent down to the denominator, so that would give me, in this case, 1 over 2x to the 1/2 power, or 1 over 2 square root of x, if you put it back into a radical form. Either of those would be acceptable answers. And we would treat the example D similarly. Okay, so here I can take the function g of x, and using my properties of exponents, I can move the x to the numerator with a negative exponent. And now we can apply the power rule. So here I'm going to say g prime of x, multiply the exponent to the coefficient, which will give me negative 1 times x, or just negative x if you prefer. And then we're going to subtract the exponent by 1, so I get negative 2 in the exponents. So again, using properties of exponents, we're going to move the negative exponent to the denominator. So this will overall give me a negative value of 1 over x squared. And so those are the first 4, and I believe you have 2 more here. So let me scroll down a little bit. I believe you have these. Oh. Nope. I don't know why I have that written. I must have never deleted that from when I used this presentation before. There they are. There's the other 2 examples. So go ahead and pause the video, work these out, and see if you can figure out these last 2 on your own, and then hit play to see what the answers I have are. Okay, so here are the answers. Did you get the same things that I got? Hopefully you did. If not, you might want to take another look at the work that I'm doing here. I'm, again, using properties of exponents to move the variables from the denominator to the numerator, and then I am employing the power rule, and then I'm going to use the properties of exponents again to make sure any negative exponents become positive by putting them back in the denominator. So let's move on here. Now this is here, the difference between the power rule and the general power rule really is just the name. Because what we were doing a second ago with the power rule and what we're going to do here with the general power rule are the exact same thing, except now what you're going to see is you're going to have a value, you're going to have a coefficient that's something besides 1. Okay, so maybe it'll be an integer, maybe it'll be a fraction, we don't know. So here are the first 4, okay, and let's see, I will kind of look at example 1, or I'm going to look at example A for you, and I'm going to look at example D for you, and then I'm going to ask you guys to try and do B and C on your own just to see how you do. So here the polynomial that we have, we just have 3x squared. That's just the quadratic parent function with the vertical stretch of 3. We're still going to take whatever the exponent is and gets multiplied to whatever coefficient is there. So the 2 and the 3 multiply together to give you a 6x, and the exponent still drops by 1, so if I subtract that by 1, I get 6x to the first power, or you just write it as 6x. So that would be the derivative for A. Now on G, again, we're going to kind of use our properties of exponents here, where I'm going to say g of x. I'm going to rewrite this so it'll be 3 times x to the negative 2 power. And then we'll repeat, similarly to what I did in A, the negative exponent, or the negative 2, is going to get multiplied to the 3, giving me a negative 6. Now in this case, when I subtract the negative 2 by 1, I'm saying negative 2 minus 1, so that gives me a negative 3 exponent here. So we will move that exponent back to the denominator, giving me a negative 6 over x to the 3rd power. So go ahead and pause the video, try to do example B and C, and when you hit play again, my answers will pop up and you can see how you did. Okay, so here are the answers for B and C. B is working very much the same way that A did. So we have s prime of t is negative 15t squared. That would be the derivative. And the derivative on C is either going to be 3 over x to the 1/2 power or 3 over the square root of x. Either of those ways of writing it are equivalent to each other, so either of them would be perfectly acceptable answers. So now we have 2 more, I believe, to look at here. And I'm going to go ahead and try to do these for you, particularly F. That one's going to be a little bit interesting if you don't remember how you're really converting your radicals. So let's just go ahead and work through these together real quick and see what we end up with. So E, example E, first thing I'm going to do on the function is I'm going to use my properties of exponents and my ability to convert radical numbers into exponents, as I'm going to rewrite this to be 4 times x to the negative 1/2 power. Generally speaking, anytime that you have a radical, you're going to want to convert it into an exponent to be able to use the power rule on it. So now we're going to say f prime of x. And here we multiply the negative 1/2 exponent to the 4, giving me a negative 2x. Negative 1/2 minus 1 will simplify to be a negative 3 over 2. So now we will use our properties of exponents to move the negative exponent to the denominator. And overall, my expression will be negative, and I'll have 2 over x to the 3 over 2 power, or you can write it as negative 2 over the square root of x cubed. Either of those would be acceptable. And so for the last one here, it's going to be pretty similar. And I'm not going to skip the first step here. We're going to say y is equal to. So I have negative 8. So here I'm going to just make sure everybody understands how we're converting the radical into an exponent. This value here is the denominator. This value here is the numerator. So that will give me x to the 4/3 power, just to kind of remind us how we convert a radical to an exponent. So here, now I can move it to the numerator, and I'm going to get negative 8 times x to the negative 4/3, and run it through the process again. Now we're going to take the derivative, so y prime. Negative x times negative 4/3 is going to give me a negative 32 over 3. And when I say negative 4/3 minus 1, that's going to give me negative 7/3 for the exponent. Now 32 over 3 as a fraction itself doesn't simplify. So we're going to just go ahead and move the negative exponent down to the denominator. So I have a negative fraction, and I have 32 in the numerator, and I have a 3 in the denominator, and we're bringing down the x to the 7/3 power, or as a radical, you can say negative 32 over 3 times the cube root of x to the 7th power. Either of those would be perfectly acceptable answers. Pardon me. So Hopefully now you're getting an idea of how the power rule is used. You're going to be using the power rule quite a bit. Making sure that you can convert between one type of a number to another is going to be very useful whenever you have to use a power rule for derivatives. So now moving on, we're going to be taking a look at something called the sum and the difference rules. And essentially what we're doing is we're just taking the derivative of each piece. This is really where we're going to start looking at things like polynomials or just kind of an overall sum or difference of expressions. So for instance here, we have some, example A, for instance, is just a third degree polynomial. But example C, they're not giving us polynomials. But all we're going to do is we're going to look at each individual term by itself and apply the power rule. So for instance, on A, we're going to take the 3 and we're going to use the power rule on it, and that would give me 3x squared. Then I'll use the power rule on the second piece, where I take the 2 and multiply it to the 5 and then drop the exponent by 1. So that'll give me a minus 10x to the first power. And then here the exponent is 1, so when I multiply the 1 to the 2, that gives me a 2, and if I drop the power on the exponent here by 1, that'll give me to the 0 power. So x to the 0 power is just 1, so we just leave it, 2 times 1 is 2. And the derivative of the constant negative 7 is 0, so we don't write the 0. So this is the derivative of the polynomial. Okay? Now I'm going to go ahead and do example D also for you, and then I'm going to ask you guys to try and do B and C on your own, just to make sure that you're doing everything correctly. B is going to be done pretty much the same thing as A. C is going to be done very similarly to what we did on the other examples, where we just convert the radicals into exponents and then use the power rule. But this one here, the reason why I wanted to take a look at this one is I'm going to rewrite this as just 4 times x to the negative 1 power. And so now we're going to just start using the power rule on each piece. So the derivative of 5x to the positive 3 over 2 power is going to give me 15 over 2 times x. And when I drop that by 1, that'll give me to the 1/2 power. And then negative 6 times the 5/3 exponent is going to give me negative 10, because that'll give me 30 over 3, so that'll simplify to just be a negative 10. And then when I say 5/3 minus 1, that'll simplify to be an exponent of 2/3. And then the last one, positive 4 times the negative 1, will become negative 4x to the negative 2nd power. Now, since they didn't give me the problems or the numbers in example D in radical form, I'm not even going to bother trying to convert them into radical form. I'm going to just leave them as the exponents with the fractions as they are. The one thing that I will do is I will move the x squared, or the last term that has a negative exponent, we'll move that x to the denominator. So here, this would be y. Why isn't my pencil working? Hold on a second. All right, well, every now and then technology just reminds you that, hey, we're fickle too. So here I'm going to get y prime is equal to 15 over 2. And if you want to write that as a decimal, that's fine because it's a nice decimal. X to the 1/2 power minus 10x to the positive 2/3 power. And here we'll get minus. Okay, my pen's acting up again. 1 second. Okay, let's see if the pen keeps working now. So here I'm going to say minus 4 in the numerator over x squared in the denominator. And so there is your derivative on D. So at this point, pause the video, work out example B and C, and when you hit play again, my answers will pop up and you can compare our work. All right, guys, there are the derivatives for B and C. Hopefully you're able to get those answers okay. If not, please make sure you get in touch with me so that way we can kind of talk them over with each other and get you on the right track. Now, moving on here, I believe we have two more basic examples of, nope, I moved those around, and here are the last two. So here we have a couple more examples, and we'll go ahead and work these out together as a group and just make sure everybody's on the same page with these. So the first thing that I want to do on example E is I'm going to rewrite the equation function h of x, so everything is in terms of an exponent that I could actually use the power rule with. So I'm going to say 3x squared minus 4x to the negative 2 power plus 2x to the 1/2 power, and now we'll go ahead and run through the power rule on each piece of the function. So h prime of x here, I will get 6x to the first power plus 8x to the negative 3rd power, and then plus 1x to the negative 1/2 power. And again, using properties of our exponents here, I'm going to wind up with 6x plus 8 over x to the positive 3rd and plus 1 over x to the positive 1/2. So there's the derivative for function h. And the last one on example f here, well, the x in the denominator, that's essentially just a common denominator to everything. So that's like, 8x cubed over x plus 4x squared over x. So you can kind of see how these are going to start simplifying using our properties of exponents. Now the last term, they don't really simplify. So we're going to just say the first term would be 8x squared. We want to simplify it if we can before we do the derivative, plus 4x. And the last one doesn't simplify, so I'm going to just write it as minus 3x to the negative 1 power with my properties of exponents. And now I can use my power rule to start taking the derivative. So I'll get 16x plus 4, and then the sign will change on the 3 because the negative 3 and the negative 1 becomes positive 3, and that'll become x to the negative 2 power. So the last thing that we really need to do is just move that negative exponent down. So the final derivative is 16x plus 4 plus 3 over x squared. Hopefully by now we're all getting a pretty good hang of the derivative concept using our power rule. Things are, the derivatives are going to get more complicated than this, trust me. But for now, hopefully you're able to say, okay, well, that's great. I can actually do the derivative without having to use that ugly, limit definition of the derivative. So here, what we see are the three basic trig functions, sine, cosine, and tangent. These are ones you just need to memorize. What they're doing is they're just giving you the derivatives of sine, cosine, and tangent. So the derivative of sine is cosine, the derivative of cosine is negative sine, and the derivative of tangent is secant squared. Okay, those are just going to be the basic trig things that you're going to have to memorize. Now we'll work through the, we'll kind of do like a proof almost to show you why those are going to be the way that they are. But let's go ahead and take a look at the next bit here. Here in example 4, what it's telling you, as we're kind of picking up from what we were talking about for sine, cosine, and tangents derivatives, here the derivative of the sine function is the cosine function. Consider where the sine function increases, the cosine is positive, and vice versa. And so essentially what this is asking you to do, this is leading into something that we're going to be doing a lot of called curve sketching, and we talked a little bit about it in a previous lesson. So what they're showing you here is while the function of sine is increasing from 0 to here, I guess about half a pi, where that is increasing, the cosine of the derivative, the cosine, is going to be above the x-axis. When the derivative starts, or when the primary function, in this case sine, starts decreasing, well, that function, its derivative, is beneath the x-axis for the same interval. Where the function, let's see, try this green here. Here, we're from pi to 3 pi over 2, where it hits its minimum at -1. Again, it's under that same interval is going to be below the x-axis. So anything that's decreasing on the function, its derivative needs to be below the x-axis. Anything that's increasing on your primary function, its derivative needs to be above the x-axis. So here, even though this on the sine function, we're below the x-axis from 3 pi over 2 to 2 pi, because you're increasing on that interval, its derivative needs to be above the x-axis. And that's just kind of, some strategies that we're going to be looking at for, if I give you the graph of a function, can you create the graph of its derivative or vice versa? But we'll definitely be practicing a lot more of curve sketching in the future, so don't worry too much about it right now. Here, what they're looking at is they're just kind of taking a look at it on a calculator where they're actually typing in, okay, well, so on the left side, you can kind of see that they're typing in the derivative of sine of x, and the graph that's produced, what you see is the cosine of x function as its derivative. And the easiest way to identify, to tell the difference between sine and cosine is sine starts at the origin, whereas cosine starts at a +1. So if you have a graphing calculator, go ahead and play around with it and see what you see. But now what we're going to take a look at, this is where we're going to get into our, we're going to be getting into our, proofs or our justifications about why we're going to be able to say that, the derivative of sine is cosine, or the derivative of cosine is going to be negative sine, and so on. Okay? So here, what it's asking you to do is we are going to look at the limit definition one more time in order to be able to do it, to show what why that's the derivative. Now, down here at the bottom, what we have for sine of x and sine of x plus h and cosine of x plus h, essentially what these are coming from pre-cal. These are angle sum and difference identities. So that's what these two things here are. These are angle sum and difference identities. These aren't things that I would necessarily expect you to need to know for a calculus course. This is about the only time that you'll probably see it in this class. We just need to make sure that we understand it. Now in pre-cal, x and h would have been angles, like theta, alpha, beta, gamma, something like that. Some of those Greek letters that represent angles for both sine and cosine. So the angle sum and difference identity is for sine will give us sine of the angle times cosine of the second angle plus cosine of the first angle times sine of the second angle. And for cosine, the angle sum identities will give us cosine times the first angle times cosine of the second angle minus sine of the first angle times sine of the second angle. And we're going to use that with our limit definition here to show what the derivatives are actually going to be. So you don't just have to take my word for it, so to speak. So here, we're going to go ahead and start looking at this. And I have this kind of typed up already for us here. So hopefully it'll go a little bit smoother than me writing it out. Okay. So the first thing I'm going to do is I'm going to take the limit definition of the derivative, and we're going to just plug in our stuff there. So we have sine of x plus h minus sine of x over overall h. Okay, and keep going. So what we're going to do is I'm expanding, or essentially what I'm doing is I'm taking the sine of x and I'm going to kind of distribute it into, well, I'm sorry, I'm not distributing it. I'm utilizing that angle sum identity. So essentially from where it begins of sine of x to where it ends here at sine of h, but right before it says minus sine of x, all of that stuff, the majority of the stuff in the numerator is just that angle sum identity. Now what we're going to look at here is that we do have sine of x as a common factor that we will factor out. So when I factor out the sine of x, I'm going to wind up with this expression that says sine of x times cosine of h minus 1 plus cosine of x times sine of x. So essentially what we're doing is we're kind of taking that sine of x at the end and the sine of x times cosine of h at the beginning, and we're factoring the sine of x out of there to get the cosine of h minus 1 factor at this point in the operation. Okay. Now, continuing from here, we're going to split it up into two separate fractions because h is a common denominator. And at this point, what we're going to recognize is that now we can start utilizing some of our special trig limits. So on the left side, there we go. On the left side of the problem, cosine of h minus 1 over h, that's the special trig limit for cosine where it simplifies to be 0. So if that ratio simplifies to be 0, 0 times sine of x overall gives me a 0 for my first term. And sine of h over h, that also simplifies to be a 1. So 1 times cosine of x is just cosine of x. And so 0 plus cosine of x is just cosine of x. And that's how we show that the derivative of sine is cosine. Now the next one is going to kind of go into do the same thing with showing that cosine is going to be that negative sine of x is going to be the cosine of the derivative of cosine. I'm going to just ask you guys to go ahead and pause the video for a second and see if you can try to work it out using that limit derivative. And then when you're done, hit play, and I'm going to have my work kind of up here so you can kind of copy it down if you need to. So were you able to get there? I hope so. So we start off with the limit definition like what we did on the last example. So I have cosine of x plus h minus cosine of x over h. Using the angle sum identity, we can rewrite the cosine of x plus h as cosine of x times cosine of h minus sine of x times sine of h. And very similarly, we're going to recognize that cosine of x is going to be a common factor in the numerator. So I'm going to factor that out, giving me cosine of x times cosine of h minus 1 minus sine of x times sine of h. And at that point, we're going to break it up into two separate fractions where h is a common denominator. And again, we're going to see that we have our special trig limits where cosine of h minus 1 over h simplifies to be 0. Sine of h over h simplifies to be 1. So the overall fraction on the left becomes a 0, and we're left with minus sine of x times 1, which is just sine of x. So 0 minus sine of x is negative sine of x. So that is how we're using the limit definition of the derivative. Am I going to ask you to do this on a test or a quiz? No. I am going to simply expect you to understand that these are their derivatives, that the derivative of sine is cosine, the derivative of cosine is negative sine, and the derivative of tangent is secant squared. You may need to remember what the derivatives of the others are at some point, but usually we can kind of work those things out in terms of sine and cosine anyway. And here, that is, I don't know where the rest of the page is. It's supposed to, that's what we're filling in at the bottom of your notes, where it says the derivative here. It should say something like, it should say something like f prime of sine of x is equal to cosine of x, and this should say something like f prime cosine of x is equal to the negative sign. I don't know why the rest of that stuff is missing, but that's what it's supposed to say. That's at the bottom of your page. Now we're going to be taking a look at the derivatives of logs and exponents, and some of these are going to be really easy to remember, and some of them are going to kind of bug us a little bit throughout the year. Here, the derivative of y is equal to e to the x. This is the only function that has itself as the derivative. So here what they're kind of showing you is if f of x is equal to e to the x, then its derivative is the same thing, e to the x. Now at the bottom what it's giving you, it's telling you the natural log, okay? And that's mostly what we'll be looking with, is with our logarithm stuff, it'll probably be natural logs. So if you have a function where the natural log of x is your input, then its derivative is 1 over x. And we'll get into this here in a minute. But let's go ahead and take a look at a couple of examples and see what we have. And this is really where we're going to kind of start finishing up what we're doing here. I think these are our last examples. So using the laws of logarithms, find the derivatives using the following. And I'm going to just kind of work through these together as a group just so we can kind of get them all done. The natural log of x to the third power is going to be, where did it go? There did it go. Oh, my pen isn't working again. All right, pause. Okay, well, I had to pause for some technical difficulties that I was experiencing, and I paused a little bit longer than I anticipated. So hopefully I didn't lose my train of thought too much. We're looking at finding the derivatives of some logarithms or some exponents, meaning like particularly something dealing with e. So let's go ahead and take a look at these, and feel free to try to work ahead of me and pause the video and then play the rest of it and see what you come up with compared to what I have. But the first bit here, a, that's really the easiest one to take a look at. Using our properties of exponents, we can move the 3 in front of the function. So here I can say, oops, and I have a highlighter turned on. So back to where we were. Let's look at the pen now. So here we have our function, and our properties of logarithm says I can take the 3 as the exponent and put it in front of the logarithm as a multiplication, and now I have 3 times the natural log of x. Well, this bit here, when I take the derivative, when I say f prime of x, that's just 1 over x, and it's going to get multiplied to the 3 that we have in front. So the derivative, excuse me, is just 3 over x for this one. Moving on to example B. Here again I'm going to use the properties of logarithms a little bit, and I'm going to separate the product that's inside of the parentheses to be the natural, and I guess I should kind of actually keep my, oh, and I keep hitting it wrong. There we go. Let's pick another color here. I should actually write my function g of x is equal to the natural log of x squared times, or not times, but plus the natural log of e to the x power. So similar to what I did on example A, the exponent for the where it says x squared, I'm going to put the 2 in front of the logarithm. So I have 2 times the natural log of x. And I'll do the same thing for the other half. I'll take the x that's in front of the logarithm, and I'll say x times the natural log of e. And now we can start simplifying a little bit. The natural log of e, here, this whole thing, natural log of e is just 1. So that would simplify to be 2 times the natural log of x plus x. And now we can start taking the actual derivatives. So here, very similar to what we did on the last example, the derivative there is just 1 over x, and it's going to get multiplied to the 2 that's already in front of it. So that would be 2 over x for the derivative of the logarithm, and the x is just going to have a derivative of 1. So here, g prime of x is 2 over x plus 1. Moving on to C, and I'm going to clear these out so I can slide it down a little bit and give myself enough room to write. So let's take a look at C and D. Here, natural log of x. First thing I'm going to do with the subtraction piece of the 1 over x is I'm going to move that to the numerator. So I have h of x is equal to natural log of x minus x to the negative 1 power. And now we can start taking the derivatives of both pieces. So h prime of x, natural log of x derivative is just going to be 1 over x. And here we're going to use the power rule. So the negative 1 and the negative that's in front of the x will become a positive 1 times x to the negative 2 power. So moving the negative exponent to the denominator will give me 1 over x plus 1 over x squared for my derivative. And the last one that we see on the screen here, D, there are 2 more that we're going to take a look at, but D here, again, properties of logarithms is I'm going to separate this to be y is equal to natural log of 2 plus the natural log of e to the x power minus the natural log of 3x. And actually that can be broken up a little bit because the 3 and the x are a product. Minus 3 plus the natural log of x. And since both of those are in the denominator, I'm going to put those in parentheses to show how the properties of logarithms are being applied. So now y is equal to natural log of 2. And here, for natural log of e to the x, I'm going to put the x in front of the natural logs using properties of logarithms. So that'll be natural log of e minus natural log of 3 plus natural log of x. Okay, so what do we have next? The natural log of 2, if I try to take the derivative of that, the natural log of 2, that's a constant, so the natural log of 2 is going to have a derivative of 0. So y prime, the derivative here is 0. Natural log of e simplifies to be a 1, so the derivative of the x is going to be a 1. The derivative of natural log of 3, again, that's a constant, so that's a 0. And the natural log of x is going to be 1 over x. And I didn't get my sign right on that. Somebody is probably screaming at me right now saying, Mr. Pierce, you didn't get your sign right here. This is supposed to be a negative here, so that's a negative there. There we go. Now I think it's right. And so finally we'll have y prime is equal to 1 minus 1 over x for my derivative on D. So now we have just 2 more examples to work through, and I strongly encourage you to go ahead and pause the video and work them out and see what you get. See if you can get to the same conclusions as me, and when you're ready, hit play again and see what your solutions look like with mine. All right, and here are the answers. How do yours look compared to mine? Clearly, we're needing to remember some properties of exponents and logarithms in order to really be able to work our way through the problems. But these are the last 2. for this particular section where we're actually looking at the actual properties of derivatives. So I hope this was informative and gives you some kind of hope at the end of the tunnel of not having a ton of difference quotients that you're going to have to work out with the limit definition of the derivative or its alternate form. But this is going to wrap it up for this video, guys. Thanks for watching, and take care of each other. Be good, and we'll see you soon.